So for this time, I'll talk about homework 3, problem 1 to problem 3, because 4 and 5 are simply solving the linear equation systems, and you can verify with the MATLAB code provided in the Brightspace. For the first question, do you have the homework with you? Okay, that's good. So for the first one, we consider a matrix whose every leading principal submatrix of order less than n is non-singular. That following the theorem 2.2 in the book, that tells us the matrix A can be will have the LU decomposition, where our L is the unit lower triangular matrix and U is the upper triangular matrix. If I write it out, the L will have one on the diagonal entry and other entries on the lower part. And our U will look like this. So we have U11 to UNN on the diagonal and other entries on the upper triangular part. So the question is asking you to show this A can be factored into the form LDU. This new L and U is not the same with the previous LU decomposition, so I'll add a star here. Basically, this L star and U star are both unit triangular matrix, either lower one or upper one. So the way we factor out everything is to, since our L is unit, right? The only one that doesn't satisfy our requirement is the U. So our U have the diagonal entry non-1. So we basically want to factor these out. So our U could be equal to the multiplication of two matrices. The first one is, again, U11 and UNN on the diagonal entries. Other part are 0. And this is our B. And the remaining part is each row of previous U divided by each entry on its corresponding diagonal. So for example, on the first row will be 1 on the first entry, and then U12 over U11 until U1n over U11. And same thing, we repeat the same thing on the second row, U23 over U22 until U2n over U22. And again and again, we repeat the process. And this will be our new U star. And this is the unit upper triangular matrix. And then later I asked you to show what is the factors of transpose A, which is A transpose. Some of you might say this is simply the transpose of LU, which is U transpose times L transpose. This is not correct, because if we write this U transpose, L transpose, this U transpose will be our new L, which is L theta, right? And L transpose will be our new U, which is U tilde. This L should be a unit lower triangular matrix. If we simply transpose the previous matrix U, the diagonal entries are not 0. So what we need to do, this is not correct. What we need to do is, since we know A is equal to L star D U star, so A transpose is equal to L star D U star transpose. which is equal to by linear algebra, is U star transpose D transpose L star transpose. Since our D is a diagonal matrix, this D transpose is equal to D. So we have U star transpose D L star transpose. Now our first and last matrix are both unit triangular matrix, and we can combine this D with something else, combine with D with the L star here to get our new LU decomposition, which is U star transpose times D times L star transpose. So this is our new L. Let's call it L tilde. And the later one is our new U, which is U tilde. Alright? So this is the first question. So the main idea for this, the first one, is to find the difference between the unit triangular matrix and the triangular matrix. The second one, we say matrix A is non-singular and show by induction. Following the theorem 2.3. 2.3 is listed on the book to show that A can be factored by, we can do pivoting LU decomposition, PA equal to LU. The difference with what we learned in the lecture is this L is no longer the unit lower triangular matrix. Instead, this U is the unit upper triangular matrix. And we will show step by step. Actually, one more question. Have we talked about the Cholesky decomposition in the lecture? Okay, yeah. That we might need to skip. Or I'll add something onto the homework later after finish. So by induction, let's say, as I said, the induction is we prove the first step is correct, and then suppose the k step is correct, then k plus 1 step is correct. So for matrix A, it is trivial to say if n equal to 1. We don't really need to prove it. So we start with n equal to 2. So matrix now is A, B, C, D. Following the steps, if A is now equal to 0, then we will have the L, let's say, which is the lower triangular matrix, which is E, F, G. And U now is, unit upper triangular matrix. So it's 1 on the diagonal edges, and say this is H. So 1, H, 0, 1, this is our U. And we calculate A equal to LU, and then find the corresponding number for E, F, G, H, which I'll directly write out. E equal to A. H equal to 0, 3. F equal to C. G equal to D times D minus C times U over A. Given A is non-zero. Okay? So we solve these by solving each entry of matrix A is equal to each entry of L times U. And then if, how about here? If A is equal to 0, since we have the assumption in the problem that matrix A is non-singular, so if A is not equal to 0, C has to be equal to, if A is equal to 0, C is not equal to 0 for sure, right? Otherwise, the matrix is singular. So we know C is non-zero. And then we can do the pivoting here, where P is equal to 0, 1, 1, 0. This pivoting matrix will exchange row 1 and row 2, and making our matrix A into CD, AB. And we follow the step previously. So we prove for n equal to 2, this is true. This is our first step. Maybe I can write on this board. Now let's suppose